Yes. Hello, everyone. I'm going to tell you a little bit about MetaRocq today, which is both a metaprogramming library and a mechanization of some variant of the theory of Rocq in Rocq itself. This is joint work with a lot of people. Yes, but the main Rocq team here. These guys, some of them are actually here today. So Leven, Matthieu, and Yannick, for example. First, a little disclaimer through the talk. Rocq is going to be equal to Coq. I might say Coq instead of Rocq. I'm going to use this to images interchangeably. And another disclaimer is that this is going to be kind of an experience report on a mathematical library, quite different from usual mathematics, I would say. And more obvious to other computer science, I would say. And I try to draw some conclusions on after 7 years into the project. What can we conclude about support of the proof assistant for writing large libraries? So a bit about the setting. So we are working with a Rocq proof assistant, which allows you to verify computer programs as well as theorems. For example, the concert C compiler verified in Rocq, the four-color theorem. From this, you also get, through an extraction mechanism, a verified C compiler executable in OCaml or Haskell, for example, or a verified coloring program, or a verified web server if you manage to formalize the workings of a web server in the system. So this relies on two main components of the proof assistant: the type and proof checker, which ensures that your formalization is correct, and the extraction mechanism, which translates formalizations into executable code. And what will contribute is a new project called MetaRocq that contains a verified Rocq type checker that we can extract then. And also two components, certicoq and what I call Rocq malfunction, which are verified versions of the extraction mechanism itself, which can also be extracted. And you can bootstrap extraction this way. So we get a verified compiler from Rocq to C or OCaml, for example. The main question we asked ourselves and when starting the project is how to improve the trust in the system. Because we find that Rocq has some critical bugs from time to time that might endanger the consistency of the system. So what do you trust really when you trust a Rocq proof? Well, you trust a dependent type checker for a quite complicated calculus that's been developed over 35 years. The implementation has been developed over 35 years. In the trusted core, you have support for co-inductive families with a guard checking algorithm, universe cumulativity and polymorphism, an ML-style module system, which is quite complex, which takes a big part of this 20,000 lines. Various conversion checkers that are more efficient than a naive conversion system that we just reduce to normal form. And extraction, if you also extract your programs. And of course, all this is implemented in OCaml, so you need to trust OCaml's runtime and compiler in some cases. Okay, so the reality is that this implemented Rocq is actually quite different from the ideal Rocq that you might imagine, or what Rocq should implement. In one way, because it's not very well specified what the ideal theory is, and in the other way, because the implementation is actually buggy. So when you add the new features, you don't have a guarantee. There is no formal proof that you're not endangering consistency, subject reduction, transitivity of conversion or anything like this. Why is it like this? Well, it's been developed for almost 40 years. We only have a kind of semi-formal and partial reference manual that presents the theory. The theory is really spread out over research work over this 30 or 40 years. For each feature, you have many PhDs that were written about the design. Of course, you have discrepancies with your OCaml implementation. Sometimes the PhD student did write thesis but did not do the implementation, or things were updated in the implementation without being updated in the formal specification. And of course, when you combine all these features, you get new behaviors, weird behaviors, buggy behaviors. So it is specified, and of course, we get bugs. We have a long list of critical bugs that were found over the years. You can look at this list, which is regularly updated. It was updated again last week because of 2 bugs found in the guard checker. Well, it's not ideal. So the situation today is that we have a difference between what we think of what ideally Rocq would implement and the actual implementation. And what we want to do here is move this trust in a core type checker into a trust in some theory that is formalized itself in Rocq, such that the ideal and the implemented Rocq implement exactly the same theory. So how do we do that? We formalize Roqq's calculus, which is called Pickwick. We verify some core algorithms like type checking in Rocq itself. This is all implemented in the proof assistant itself. And through some magic of bootstrapping, we can actually verify this formalization a priori in the bootstrap system. And then we have complete equivalence between the implementation of our proof checker and the specification that is formalized. Throughout, to do actually that in practice, we also need to verify the extraction mechanism to get runnable code out of Rocq. And that's also part of this. Okay, so outline of the talk is that I'm going to give you a tour of MetaRocq, display, do a little demo of the metaprogramming facilities, go into more detail into how do we formalize the meta theory and the verified implementations, and then reflect on some of the formalization challenges we had. Okay, so MetaRocq is about 250,000 lines of code. So it's a rather large library in Rocq that is decomposed into a few components. The first and smallest ones and most visible ones actually to users is template Rocq, which is a metaprogramming library which allows to manipulate terms, declarations in the environment, to do a metaprogram that add declarations in the environment of Rocq. Then we have the meta theory of Rocq in Rocq. So that's a Rocq development for some typing judgment, basically. And that takes up a large amount of the work. Then we have a type checker that is an implementation of a type checker for the theory that we developed previously. An erasure procedure that goes from Rocq terms to untyped lambda calculus, basically, and a proof of correctness of this translation. Then there is a small library of quotation, which is a formalization of Loeb's theorem for the typing judgment of Rocq, which I'm not going to talk about too much here. And on top of this, we have a verified extraction. So erasure just goes to untyped lambda calculus, but we actually want to go to a real programming language to execute our programs. So we translate from this down to OCaml. And we also verified this extraction. And if you actually extract the whole formalization, you get about hundreds of lines of OCaml code this time. But extraction is not great at not duplicating code. So a bit of history on MetaRocq. So it started as a very small library called the template code, which was developed by Gregory Maleka, who did his PhD on doing reflection time series and reflexive tactics in particular. And while his main work revolved around the reflection of system F, he also tried to lift his work to a more specific calculus, like the calculus of construction. So he implemented a reifier for the ASTs of Coq and a denoter. So all these are meta programs that are written in OCaml. You give them a code term, and it provides you a syntax in an inductive type defined in a of the term. And it had minimal metaprogramming support. And then we embarked in this theoretical project whose goal was to compile Galena code to C code in a verified way, so a verified compiler for Galena. And the first step of this compiler is, of course, to do erasure to untyped lambda calculus. So at the beginning of the project, we use a completely untrusted, very hacky erasure procedure. And we extended a little bit the metaprogramming support in template to achieve this, to start writing this compiler. Then we realized that to actually prove anything about the compiler, I mean, if we wanted to have some real knowledge that the compiler was correct, we would need to verify this erasure procedure itself, and that would mean we would need to formalize the whole theory of Rocq, the typing judgment in Rocq. So we started doing that in 2016, 2017, and it took us 6, 7, 8 years maybe to get to a full meta theory and verified checkers and a verified erasure procedure. And then after that, we added the extraction to okay, so a little more to show you what it looks like. Sorry, I'm a bit lost. Okay, so this is basically the term AST of Rocq with very minor differences. We have exactly the same amount of the same constructors as in the Rocq implementation, including a match and fixed points. We have the standard lambda calculus operators. You can see you have the lambda abstraction, Latins, applications, constant and inductive references, constructors, case analysis, projections, fixed point, cofixed points, and primitive integers and primitive floating points. And variables we have two kinds of variables. So double variables, T-var here, and name variables, T-var, but T-var is not under in our formalization.
The TR takes a list of terms for the arguments?
Yes, so that's a representation that's used in the Rocq implementation. Actually, lists are arrays in OCaml representation of the data type. We transform them to list, but we do all the meta theory on a binary application representation, which is much more, much greater for specification. But we show an equivalence of this system and typing rule for this system with the NRE application with the one with binary application. We have translations back and forth. Okay. So then we have commands that are provided by MetaRocq. You've seen MetaRocq run being mentioned in the previous talk, which allows you to run a meta program. The basic building blocks of this are a quoting mechanism that allows to get the syntax of an expression. So if I print the definition with X, it's the AST corresponding to the Rocq definition here. And we have the converse. If I can give some AST for well-typed term, then I can denote it. And here, this is a reference to the first constructor. I mean, constructors are starting from 0. First constructor of second constructor of natural numbers, sorry, which is the successor. Okay. Simple. To work with this, we have a monad that is a free monad on a set of comments that you can send to the MetaRocq plugin that allows you to communicate with the Rocq kernel itself. So you can print things, you can return an error, you can evaluate sometimes. So we basically binding to the OCaml API as you would have in a tactic language ability to communicate with the system. And through this this monad, we can write larger meta programs like this one here, which says, oh, my program will just declare lemma with some name. We should have the type of natural numbers. Then I'm going to ask the users to fill this lemma. So give me a witness for a natural number. Then I'm going to quote as a result of this in the content of this lemma, evaluate it, and then print it. And I think you can see it here. So the user is going to be asked to give a witness for a natural number. It's going to be 3 plus 2. Then the meta program will evaluate 3 plus 2 to 5, and then it will print it. So you'll see the result 5. Okay. Then we will have in the library all this specification of Roqq's type theory. So in particular, we have the typing judgment, which is a standard inductive definition with all the rules of the calculus. And on top of this, which I will present next in the slides, is the meta theory of the system. So proofs of subject reduction, of confluence, principal typings, the fact that we have canonicity allows us to show that if we can type a term in an inductive type in an empty context, then we can reduce it to an actual constructor, things like this. Okay. I'm going to see on the checker. As we have this mix of working in the theory and in the meta theory, we can write a complex meta program that actually build typing derivations, and we can even call the verified safe checker and safe conversion algorithms inside Rocq itself to build typing derivations. When you know you have a well-typed term, you can get a well-typing derivation from calling the safe checker, for example. We can use that to write interesting tactics. And of course, the safe checker and the safe erasure that we define are also available as plugin that you can call from Rocq itself. So here, this command actually calls the safe checker. So it's useful to compare the results of this with the actual Rocq kernel checker. Okay. Any question on this? So let's see what we really have formalized here. We represent the whole syntax of Rocq. So that includes fixed point constructions, the case, the dependent analysis construction, on arbitrary inductive types. So we represent parameters, non-uniform parameters, indices. Let bindings are everywhere. We also have the universe hierarchy and polymorphism. We also have the fact that inductive types can be cumulative for universes. All of this is represented in the typing code. We also have a specification, of course, of reduction, plain one-step reduction. It's contextual closure, it's reflexive closure, transitive closure, many variants of reduction defined. One important difficulty in this formalization that I did not foresee when I started is that verifying the actual implementation of this theory means verifying the theory of lead bindings, of dependent lead bindings. So it's just an extension of the standard judgment on context, where instead of just having assumptions to serve definitions, but they can be unfolded anywhere. You have a general substitution operation. And you can reduce in the body of lead binding. And in the course of that reduction, you can actually unfold the value here. So you have kind of two ways to reduce lead binding. Either you just expand it, which is a traditional way to think of lead bindings. But as things are dependent here, it might be that the body here needs to actually unfold X to reduce the B prime. Okay, and this kind of reduction at a distance makes statements and reasoning on typing and invariance of substitution much more complex. And I don't know of any library that can, that handles that complexity before. Okay. So back to the structures, we've seen the definition of terms. So in the meta theory, application chain is actually binary to simplify our life. We have not only terms, but also global declarations that we must work with. So declarations of constants or inductives that are just, can also just be quoted from the representation in the Rocq kernel. So they just associate a kernel name, which is a unique identifier to a declaration. The bodies of a constant can be empty if the constant is actually an axiom, or it's defined to be some term if the constant is actually defined. And then a global environment is not just a list of declarations, it also has a declaration of universes, which are the global universes defined for this environment to type check. And as I said, local environments are not just assumptions, you also have net binding. And on top of this, you define a few judgments, so reduction, disclosure, you have notions of wicked reduction, call by value reduction that are also defined, and you must show equivalences between them. We have a notion of alpha equivalence, which is extended with the comparison of universes. And we not only have equivalence, we also have cumulativity, which is a set of that universe I must be less than or equal to universe J, and this lives through pi types. Then we can define different variants of the conversion judgment, or the cumulativity judgment in general. We will show that it's equivalent to untied reduction and comparison with alpha equivalence. The judgment of typing, which uses the previous ones, and notion of well-formedness for a global or local environment. So the basic meta theory and structural properties. So we have a simple representation based on De Bruijn indices. That's fairly common in meta theory studies in proof systems. So there's nothing very surprising here. We have traditional De Bruijn lifting and substitution operations, as in the Rocq system. But thanks to the experience on AutoSubs, we also found out that it's much easier to reason on the abstract schema calculus presentation of these operations. So we also have this instantiation and renaming operations and all the theory on these operations. We can show equivalence between listing and substitution, which is what is actually used in the Rocq kernel, to these versions, which are useful for formalization, but you would not want to actually implement renaming and substitution and instantiation in the kernel, because you would be carrying closures everywhere, which would be terrible for performance. So we still have both of these operations. Let me show the examples. And we can show that all our derivations support weakening substitution from actual more generic renaming and instantiation limits. And we can also, thanks to this renaming and instantiation presentation, more easily show lemmas like strengthening, which are difficult to show with just lifting and substitution, which do not express strengthening. Then we have our notion of universes, which are proposition, strict propositions of types, where a type takes as argument an expression which is a non-empty list of universe level expressions. So max u plus 1 v, for example. We have a slight difference from the current theory of Rocq, which is that our rule for sort, that if you have some sort u, then it lives in the sort at u plus 1. And there is no distinction in the system of the fact that universes might be algebraic or not, which is something that you might not know about, but that implementers of Rocq know about. In the API of the Rocq kernel, if you call type inference, you get a term which might be a type with algebraic universes in it. So it might be of the form max u plus 1v. And that kind of terms cannot be put back in the subject position of a typing logic. You cannot ask the system to infer what is the type of max u plus 1v. Okay. So you need to do that, to work with that, around that. You need to refresh this max u plus 1v to another variable, v prime, that is greater or equal or smaller than this one. And then you can ask what is the type of that fresh universe. And this has to do with the system of constraints of universes. So we avoid this complication entirely here. We can take successors of universes arbitrarily, and they are well typed. Then we have a notion of universe constraints, and the specification for a universe constraint system to be valid is just that it satisfies the valuation in the natural numbers. We will need to implement also algorithm to check for this consistency. We can show basic weakening and universe instantiation operations. So universe substitution is actually just instantiation. We don't have a notion of lifting. There is no a local weakening for universes. So it's a fairly simple thing to implement. We actually use De Bruijn levels rather than indices to code the universe variables. And there is no capture, so the lemmas are pretty easy. And then we implement a very naive constraint satisfiability checking algorithm for the set of universe constraints, which takes just the longest simple paths in the graph generated by the constraints. And we need to show that it's correct and complete for this. Once we have that, we can think of proving more interesting meta theorems like subject reduction. The traditional way to do this is first to prove validity or generalization lemmas. So this says that if some term little t has type big T, then T has some sort S, which would not be true if I did not have this ability to take the successor of any universe. We have a general context conversion lemma. Actually, it's more like context cumulativity because we have contravariant notion of equivalence of context due to contravariant subtyping of pi types. And then when we have that, we can try and prove subject reduction. So the fact that types are preserved by reduction. But validity actually requires transitivity of the conversion or cumulativity notion. Subject reduction requires injectivity of type constructor. So if you have two pi types that are convertible or in cumulativity relations, then you have cumulativity on the domains and codomains, which is going to be a consequence of the confluence lemma for notion of reduction here. So we must formalize confluence. We do it in a pretty traditional way. We define parallel reduction, and then we need to show a diamond lemma for parallel reduction. And then you have this usual squash lemma that says a one-step reduction is included in parallel reduction, which is itself included in the transitive closure of one-step reduction. So it must be confluent as well. But we have context with definitions, and we need to actually generalize the notion of confluence to not talk only about the terms, but also about the context, because you might have reductions in here in the definition little t of x that happens in parallel with reductions in the actual body V. And to prove confluence, you actually have to prove confluence of the whole set of reductions in the context and the term, which was a slight complication. So what do we need to trust in this formalization is actually just the notions of typing, reduction, and cumulativity, the specifications of these notions, which are around 1,000 lines, so pretty succinct. The rest is derived from this. And I should say that we have right now oracles for the guard condition. So we don't formalize the guard condition. We expect that we have an oracle that takes an environment, a context, and a fixed point expression and tells us, is it a guarded recursive definition or not? Assuming that this oracle also preserves all the operations of substitution and substitutions, and so on. So we are working on actually removing these oracles and trying to formalize a guard condition and show its correctness to remove this assumption. So what does it take to verify the type checker? Based on this, we need to implement conversion. So it takes as input two terms that are well typed a priori. It might be that they are typed in different types. And then we need to show that either they are convertible or not. So we need just a decision procedure for the convertibility. Actually, if you formalize this in MetaRocq, you take not only the terms and the terms U and V, but also two types A and B, judgments that they are well typed, and then you return a conversion proof or possible. I mean, it's correct and complete, so it decides conversion of U and V. And the algorithm is more subtle than just going to normal forms and comparing them. We take their wicked normal forms, we match on them. If they have the same heads, then we recursively match the components. And we do that for all the constructions, and wicked normal forms include all reductions about this system. And then we need to show also completeness. So correctness is relatively simple. Completeness is a bit more complicated. When I'm asked if two products are the same, and I found that the domains are different, I must conclude that then the pi types themselves were different, which uses some strong results of the meta theory that we've proven before from confluence. So it needs inversion, lemata in conversion and confluence property. The really hard part difficult part to formalize is this wicked reduction, because we need to do it in an efficient way. We actually have a stack machine reduction, and we need to find a termination measure for this. So assuming that we have terms that reduce as input, that are strongly normalizing as input, we must find a measure that makes this wicked normal form algorithm terminate. And that was actually designed by Matthieu in his PhD. Once we have this wicked reduction that's proven correct, we can then implement cumulativity. But to do type checking, we also need an inference algorithm, right? When you want to check that some term T has type A, you infer the type of T, it gives you some type B, you check that it's less or equal to A, and then you have your typing judgment. So we need to implement this inference algorithm. And to do that in a proper way, we rely on an alternative presentation of the typing judgment, which is based on bidirectional derivation. So basically, it splits the typing judgment into two new judgments that are mutually defined. One that infers a type T, and one that checks type term little t as okay, and then we can write the type inference algorithm in a way that is very close to the actual derivations of bidirectional judgment. This was work that was done mainly by Neven, actually. The nice thing about this bidirectional representation is that the rules aren't syntax directed. It trivializes the correctness and completeness of the algorithm because it really follows the algorithm. But of course, to show its equivalence with the undirected system, you need strong meta-theoretical properties that we have developed before. Another nice thing that we get is that the strengthening property follows directly from this presentation, which is not at all trivial from the undirected presentation. And this is a useful property to have when you implement the metaprogramming. When you implement tactics, you need strengthening. Here we have more things to trust in our theory. We don't have a proof of strong normalization, as you know from Gödel. This is probably, there is no proof of Gödel's second incompleteness theorem in the particular case of the calculus of inductive construction, but we believe that we will suffer from this problem. So we assume normalization. So it just says that for every well-typed term, we assume that reductions starting from this term are always finite. So as a co-reduction relation is accessible for this, starting from this term T. We can show consistency in canonicity from this axiom. And actually, we are using exclusively this axiom exclusively for the termination of the wicked reduction algorithm, not for any of the theories that I've presented before. So it's independent of normalization. To get away from this assumption, we will have to prove normalization for the system we are looking at, or subsystem of it. So there is work on improving that situation. To verify erasure, now that we have a safe checker for typing, we can verify the extraction of a term to the untyped lambda calculus. Erasure is a pretty straightforward procedure that removes anything that is a type annotation, but also any witness of proposition, so something that it's incorrect. So all the proofs are right. Okay. And the main difficulty in verifying this procedure is that we have a so-called singleton elimination principle, which allows to remove matches on propositions, even if we are building computational content. So if you match on an inequality to build something computational like a natural number, the extraction will forget about the typecasting that was done by the equality match. So said otherwise, when you coerce any object in some type px to py because you know that x is equal to y, after erasure, it's just the identity. Okay? Nothing, there's no computation. To show that, what we want to show from this for this erasure function is that if t erases some t prime, and t was actually evaluating to some value in the Rocq theory, then we also have a value in the target calculus for which the erasure evaluates, and they are somehow related. So the initial value in Rocq and the erase value that we computed. Thanks to the meta theory we had before, if we have some closed term T of type NAT, then from strong normalization, we know that it reduces to some natural number n, some term m that is irreducible. From canonicity and solution, we know it's also a natural number, and it's actually a succession of constructors. We need standardization to show that we can also get to this term n using a call by value reduction, which is more strict than the full reduction. And by this tabulation lemma, we also know that we can compute the same thing as through extraction. To do that, we cannot actually reason directly on the function of erasure. We need to first define a relation that represents it, but that might not erase all the subterms that it could. And we show that the erasure function is kind of optimal. It erases maximal subterms that are erasable, and it's included in this erasure relation. And from this, we can show the actual correctness. So it's also a non-trivial proof. And an additional complication is that to have a usable erasure function, you must also not erase the whole context that the term that you erase depends on, but only the set of dependencies that are actually used in the term, or actually used in the erase version of the term. So to get the minimal environment to extract your programming language. And that complicates the proof some more. Once we have this erasure tool on the calculus, we can also extract it to a camel. So here we have, so that's work that we did with Yannick Forster. We have a representation of the AST of the entire OCaml term we want to produce. And there is an existing compiler that we are reusing that takes this representation of OCaml terms and compiles them down to OCaml modules that can be linked with existing OCaml code. This malfunction system actually had a reference interpreter written in OCaml that we ported to Rocq. And we can empirically verify that interpreters agree. And then from then on, we only reason in Rocq, and there we can define a big step operational semantics for this calculus and show that it agrees with interpreter semantics. So again, we do simulation lemmas to show that starting from this untyped lambda term, we will get down to OCaml terms that behave the same as the original ones. So it's another pipeline of compilation steps. And we can compose the theorems to show that if we start from a well-typed term of type NAT that's closed in Rocq, we get an equivalent term in an additional thing that we prove for this extraction is that we can do separate compilation, because if you want to extract to OCaml, you might extract functions that are later applied to some arguments. So the theorem on closed terms of type NAT is not very useful in that situation. And to do that, we must develop some realizability semantics for some subset of OCaml types that we consider, basically just first order types. And we need to show also, as part of this proof, that all the functions that the extraction is producing are pure, even if they interact with impure functions from the OCaml world. And that's another pipeline. Okay, so to summarize the results, we have formalized our idea of what is the ideal Rocq, so our specification of the calculus, verified algorithm with respect to it, all this in Rocq itself. And thanks to the verified extraction, we can now provide a verified checker that could replace one day, when it's efficient enough, the verified core. And we have publicly bootstrapped the system. Okay, so we are in a much better situation because what we need to trust now is just the specification that we have in Rocq of flexible units. In the works are many extensions. So now it's not the policy of the Rocq development team, but it would be nice that we get there someday. We are trying to justify extensions to the system in MetaRocq or through other formalizations before introducing them in the kernel to to avoid discovering after the fact that some combination of features cause problems. There is an integration of sort polymorphism and elimination constraints that is being working on. I just completed the verification of a much more efficient algorithm for universe checking that will also be integrated. There is a lot of work that was spurred by this formulation in MetaRocq on how to deal with the most complex rules for conversion in Rocq. So notably, eta conversion for pairs and functions is not handled in the current formalization, but we hope to get there in the future. Also, definitional equivalence is a problem. Rewrite rules. The link with type equality is also stated there. And there is also a practical output, which is metaprograms for dealing with nested types. I'll come back to this soon. And in other future directions, we did not consider higher level components of Rocq yet, just the kernel, which does not handle essential variables or name variables. But if we want to verify more high-level constructs like unifications, we will need to support these notions as well. And there is Matthieu who was there yesterday. I'm not sure today. We started PhD in this. So, what time is it? Oh, okay. I try to be good. Okay. So some formalization challenges. And some reflections on what was nice in this formulation and what kind of tool support we needed. So we are working with kind of on-demand separation of computational content for this verification. So we define a squash type that goes from type to prop instead of putting everything in prop from the beginning. So our derivations are actually in type. So they are computational objects on which you can compute, for example, the size of a derivation, which is actually necessary in many proofs where you need to reason on a well-founded order on the derivations and not just structural induction on the derivation. And you can still squash it if you want to erase that content through expressions. So it's nice also in the sense that it makes it explicit in the statements where you have used squashing or where you have actual computational content. So for example, conversion does not take actual types and derivations, it takes squashed version of them. So the erased version just takes two terms and returns basically a Boolean telling us if the types are convertible or not. There is an essential use of dependent elimination everywhere in the meta theory proofs. So the ability to do induction not just on a general instance of an inductive statement, but on a specific instance of the statement. So it means, for example, here I'm inverting a proof that some application of an inductive type has a property. MCAP is a function here. So if you want to do induction on this, and you call the induction tactic, you will just forget all the information about the actual instance of the inductive. To avoid this, we use dependent induction tactics that allows us to keep this information, which was instrumental in actually verifying this. Otherwise, each time you have such a problem, you need to explicitly generalize by inequality between the thing you want to induct on and some subterm, and then you need to solve or do injectivity reasoning to resolve all subgoals, and then applying induction hypothesis is also an administrative nightmare. So that's what's important. Another thing that we use a lot is the ability to use views when you do pattern matching, in particular a dependent version of the views that we have known about in Haskell, for example, for a long time. So here, this is a function that reduces some term to a sort, and which might call wicked reduction to do so. And to program it, we actually don't look at the term directly, but a view of the term which tells us, oh, it is actually the sort constructor applied to some sort S, or it's not a sort. And then you can reason on that another difficulty is the sheer size of the formalizations. in the sense, for example, that to verify the whole pipeline from untyped lambda calculus down to camel, we have 10 or 15 compiler passes. Each one works on a slightly different syntax with slightly different invariants and slightly different evaluation relations in the source and the target. So rather than having 15 definitions of ASTs and 15 definitions of evaluation, we have just one that we make configurable, saying that we might activate or deactivate some evaluation rule, for example, or the appearance of some constructors in the input terms. And on top of this, we built custom induction principles that are parameterized by these configurations. So for this lambda box definitions, we have only one AST definition and one evaluation relation. And the nice thing about this is that we can write generic lemmas that are used in basically all the proofs of preservation of evaluation that applies in all the different situations. So they adapt to each compiler pass. So this avoids duplication, which is essential here to just make the proof efficient. Okay. Another thing that we found is that, so we have this notion of term, and it's well formed for some particular flags. So it might have some constructors appearing or not. We want to define a kind of special induction principle that combines the induction on the terms and the induction of on the well-formedness principle. And it was also very useful to avoid duplication. Otherwise, you do all this invariant passing in each of the proofs of preservation of evaluation. So we avoid that by combining the two notions. And I think it's a notion that's related to ornamentation of data types in some way. But there is no general theory of how you combine an induction principle on some inductive type with some notion of well-formedness for this type, some inductively defined notion or predicate on this type, to get automatically the right induction principle. I think there is some work to avoid this, doing this manually. Another essential feature of the assistant.
How many slides do you still have?
3, 2, 3. I should Another essential feature of the proof assistant was the ability to use nested inductive types, and not only inductive types, but nested predicates. We are making essential use of all the variants of the all predicate on list. So in many places, you need to synchronize data coming from two lists that should have the same length, and that positionally the first element of the first list and first element of the second list have some relation. This is essential to formalize this. The bad thing is that these nested types are kind of badly supported in a proof assistant like Rocq and Lean. For example, in Rocq, you need to write the induction principle of your inductive types using nested types by yourself. In Lean, the set of a nested type that is supported is too restrictive, for example, to formalize the typing relations that we have. But this can be solved. The nested types are well supported in other frameworks like Isabelle with the bounded natural functors. So we've been working on providing a more user-friendly interface to nested types that will allow the system to automatically generate the induction principle. It's a pretty common lesson that you learn when you do a formalization. Avoiding duplication and trying to find smart proof techniques is essential to make the thing feasible and to not get just burnt out from trying to prove something formally. And of course, modularity and genericity. So using polymorphism, using abstractions, finding the right elimination principles are key to avoid this duplication. I'm going to skip over related work, but we can come back during the questions. And if we want to go further, the website has documentation, papers, and samples. Thank you.
Time maybe for one question. Yes, you won.
So as a naive user, it appears you have completed much of your meta theory work. Can you explain how the recent soundness bug fits into that picture? Are there missing pieces, or is my understanding incomplete?
the recent soundness bugs in the guard checker. Sadly, as we did not verify the guard checker, we don't have, we didn't verify this code yet. I think I mentioned it at some point. But actually, the recent soundness bug were found by, because we are investigating with Thomas Lamiot and Nicolas Tabarot, how to actually define these nested recursors on inductive families. What does it really mean to have a recursor? What kind of inductive types we can really handle? In the course of that formalization, we realized maybe that this is accepted, but it should not be, and it's the case. So we found the bug this way. So it's a good impetus to try to formalize, just to think about all the problems we might encounter in the actual implementation.
Thank you. Time for lunch.
Thanks.